Aladin, thank you very much for being with us. It's really a pleasure. I was looking forward to discuss with you because you have an interesting story, I would say, right? And obviously you do very interesting work. So yeah, we should just get started. The way I typically do it is just ensuring that we have your sort of background, your CV, right? Just because we are gonna mention and refer it during the interview. So I just want to be sure I don't get anything wrong. So I'm gonna read like a little bit of a paragraph that I took note of here, and then we get started. Is that okay with you?
Sure.
Okay.
Yeah,
So Dr. Aladin Aspaye, am I pronouncing correctly, by the way, or am I doing?
That's
okay.
correct.
Perfect.
Yeah.
You're currently a research scientist and project leader at DuPont in the US. You started your study in Syria at Damascus University, where you are from originally, right? Before moving to graduate work at University of Alberta in Canada. You did your postdoc work then with William Dichtel at Cornell, where really you began all your exciting work on the sort of polymer, the high surface area polymers and three-dimensional polymers and all these sort of things, mostly for the remediation applications. And then after your postdoc, you worked at Arkema for a couple of years, and then moved to DuPont, where you're currently focusing your work on the CMP, the chemical mechanical polarization for electronic applications. I don't know if you do anything else, but we'll find out as we speak. So is that all more or less correct?
Yeah, that's correct.
Okay,
yeah,
perfect.
Thank you very much.
Okay, Aladin, as I said, it's great to have you with us today, and it's I particularly enjoy the interviews when people have an interesting story, and it's typically very interesting. It's more interesting when there's more international experience, and you are a prototype here. So I really like to start from there. A little bit of your story. I always like to kind of find the person behind the science, because there's always a very interesting link there, and I think in your case this might come across particularly strong. So can you tell us a bit more about yourself? And I am particularly interested in how did you get interested in science and chemistry in the first place?
Yeah, thank you very much for having me. It's really my pleasure. Thank you very much also for the introduction. It's kind of interesting. So I'm actually originally from Damascus, Syria. So Damascus is the capital, and it has a Guinness record of being the oldest capital in the world. So you can imagine like really tremendous history and cultural diversity in Damascus. So actually I'm really mixed a lot. So my mother's side, her father is Turkish, her mother is Jordanian. My father's side, his mother is Lebanese, and his father is Syrian. So I'm really mixed, from the Middle East, kind of from different countries. And it's Damascus is really typical in that regard in terms of the cultural diversity and background. So I think that really helped a lot in kind of shaping who we are. And I think kind of the way we were raised is kind of really kind of appreciating and kind of respecting everybody, really kind of mixing with everyone. We have a really very, very open mind in general, in my family at least, or even in, the way that like people in Damascus think or behave with each other. So when I was young, actually, I was very curious child. So I used to really kind of open electronic devices and I tried to see what's inside. I was really fascinated. It wasn't the 80s when we used to have the recording machines, and it was really fascinating to me, like how these devices work, like what's the magic behind them. So I used to open these devices and trying to see what's inside, and sometimes I used to break some of the electronic devices. So I think that what really was helpful was my father was really very kind of supportive in that regard. So even if I broke some devices or something like that, like he was very tolerant to that, and he was even encouraging me to do more of that. So that really helped a lot. So that grew further actually until to a point that I was able to fix electronic devices without really taking any formal training on that. Just kind of like looking at the kind of what's inside the devices, kind of trying to kind of really dig inside just by kind of like visual how they look. So I learned how to fix them, things like that. So that grew further actually in the 90s when we started having the computers. So I think we were the first in the family to get a computer. And I was again fascinated by computers to a point that I was able to fix hardwares, softwares on computers, and again, it's all by curiosity. Um, and I think that's kind of, and then after that, I started getting more towards science in general. Kind of, I was fascinated how by how like the scientists kind of wear these kind of lab coats in the labs, and and at the same time we're taking more chemistry courses, in the school, especially in the high school. So I was fascinated more, for chemistry. I was, kind of more interested to know kind of how matter is made of, how, the kind of like the action work, like the chemical reactions work. At the same time, also, I had my uncle. He had a PhD in organic chemistry, actually, from
Oh,
France, and he was the most successful, educated person in our family. So I was also like very inspired by him. He worked for Nestle in Syria, and then he was quickly promoted to the head of the Middle East in Dubai for Nestle, actually. So he was very successful industrial chemist as well. Very high ranking kind of. So that was, all played really a role. And then I would say the last piece of really kind of inspiration for me to choose chemistry was when Ahmed Zuwel, the Nobel laureate in chemistry, was he was in the US, but he's originally from Egypt. So he was the first kind of originally Arab person to win the Nobel Prize in chemistry. So that was actually right in the high school when I was in the high school. So right before I went to college, that was really kind of the last piece of inspiration that I got there. Yeah, I mean, I want to go to chemistry the next year. So yeah, I mean, I hope I answered your question, but
you did, yeah, absolutely.
yeah,
So you mentioned a couple of very interesting things that um, tend to be sometimes together, sometimes in isolation, part of most brilliant scientists or successful scientists. So there's curiosity on one side, and I'm going to expand the concept, in a while, because I was attending with interest your presentation that you gave at the Talented 12 award event, and you were speaking about imagination, which is a more intriguing concept. But let me get there a bit later, right? And there's also this sort of inspiration figures. You mentioned your uncle, but also the support you've got from your family in kind of encouraging your curiosity and developing further, which are extremely important aspects. So it makes for a very interesting start here, I think. And how did you get? Obviously you had the example of your uncle, with with an international experience and education. So was that the source of inspiration? What kind of inspired you or convinced you to go abroad for progressing in your studying after the university in Damascus?
yeah, that's true. So yeah, I mean, most of my family in general were are merchants. So my father even was actually one of the most educated in my family, like from the father side. So he's a civil engineer. So I would say that was part of it, right? So I was not really interested in kind of being a merchant in future, like similar to my other kind of relatives. So I think like my father, like so when I was younger, I maybe I thought about like being an engineer because like you look at your father, you become like uh, you would like to be like him. But then, yeah, like my uncle having the international experience, I think that was really powerful story that actually grew the ambition in myself that we can do it, right? So I'm not from a very rich family. My father is like, he's we are middle class. There is no way like my father can pay for my education abroad. So seeing my uncle being able to be like one of the top graduates in chemistry actually in his class, and then getting some scholarships abroad, and then studying like having getting his PhD, that actually kind of gave me some like some messages that it's, I mean, money does not really stop us from like going to where we want to go. I think that was the most powerful, like the ambition part of the thing is that's what mainly kind of played a role, kind of like having my uncle being that successful in the chemistry world. So yeah, I would say that that kind of at least you know put me in a way area where, yes, I mean, I would like to be a scientist in future, and even though my father cannot support me financially, I can try to find a way. If I'm, I really do very well in my bachelor in Syria, then I can get some scholarships and go abroad, because I know that if I would like to study chemistry, I have to go, to the US at least. US is one of the top countries basically in science and scientific discovery. So I have to go there somehow. That's how I started thinking about it during my bachelor studies at Damascus.
So no, being aware of that, having an example, so knowing that it's possible to do, right? It's a great start. But it still takes courage. It's not an easy thing moving internationally. So, and I can say that because I've done it myself. Maybe not such a drastic move from Syria to the US, but I've traveled around Europe, and going into a different country with different culture, different language is not a joke, right? It takes some skills and some courage and perseverance, right? Can you tell me about your experience? How difficult has it been? What?
Yeah, at the beginning it was very difficult. So I would say the courage, as you said exactly. So the courage is not something you can have by nature sometimes. It's something that you can learn. It might be a skill that you grow over time, from really stepping out of your comfort zone very often. That helps a lot with the courage. And I think the very first move that I had to Saudi Arabia, it was a little bit easier for me because Saudi Arabia, it's not exactly the same culture as Syria, but it's, I mean, still within the Middle East, right? So the language is almost similar language. So we have different accent, but similar language. And it's probably the most difficult thing was, this is the first time I, go like, to a different country. It was the very first time I travel, the very first time I'm away from my family. I think that was the tough part of it. So I was scared, but I think my ambition, I I knew that I wanted to be a scientist, and that's actually kind of helped a lot to really kind of encourage me, and also have some kind of courage to really take that step to travel to Saudi Arabia. But it was easier again. So probably if I went from Syria to Canada or the US, it could have been a little bit harder. But I think I took it in steps. So, my courage kind of really grew a little bit slowly, right? So I went to Saudi Arabia. That was the first time I stepped out of my comfort zone. Then, it was okay. Like during my master's, there were some difficulties the first 2 semesters, but then it was really good. And then after that, from Saudi Arabia to Canada, it was a little bit of like, it's not only cultural difference, but also the weather was very different, right?
Yeah.
So it was like, it's going from the most hot areas to one of the most cold. Especially Edmonton is one of the coldest cities in Canada. So so I think the courage somehow grew, in steps in my situation, and I think it was a skill that
you also grow as a person, right? So you're very young when you start university, and then you mature. These are a few kind of key years in a person development, and obviously as you grow older, you also get more in control of your thing. So it becomes, I'm just about saying, it becomes easier. It's never easy, right? But it's kind of easier to do it when you're in your 20s than when you're a teenager, of course, right? Yeah. Exactly. So you mentioned the weather, you mentioned the language, and obviously it's interesting how the way you commented, right? From Syria to Saudi Arabia, it's a difference. It was a challenge, but it was kind of an in-between step, and then going to Canada was a bigger step and a more challenging one. And you went from the Saudi Arabian weather, which is probably in the 50 degrees in the summer, to Alberta, which is probably 50 below zero, or close enough. And anyway, all these experiences, what have they really taught you? What do you think you got from them?
I think it was I was fascinated by the cultural diversity. That actually kind of really fascinated me the most, from all of these travels. So when I, growing in Damascus and being around my family all the time, it's very difficult to understand, other kind of people, how other people think, and how, the other people live in general, right? So yeah, I would say the cultural diversity has really taught me a lot, and I become much more interested in kind of like mixing with people from different backgrounds and learning about them, about their culture, about how they live. So I think that helped. Also, the other thing is the adaptability, right? So you become more adaptable to kind of like different environments, different research environments from scientific point of view, and also from cultural. You know more about how people think. I think that's also like very important for industry in general, right? Because in industry, sometimes you have, especially for working for international companies, like you have people from different cultural backgrounds. You need to be careful about the kind of sometimes the words, or sometimes even the time zones, and you know how you,
Oh yeah.
like some people are more punctual in time, some cultures are less, a little bit more relaxed around that. For example, there are some differences, cultural differences, and I think um, that really, like living in different countries, that really taught me of how to be more respectful of people cultures and diversity, and how they think and how they behave, being more tolerant to many of the stuff that, you know, probably we used to have less tolerance, you know, in certain kind of culture. Then you become, you know, you learn about, like, there are some things that are not as, like, you know, strict as, you know, what we used to have, for example, in Syria. So that's kind of really taught me a lot in that, and that grew me as a person in terms of respecting, you know, other people, mixing with other people, understanding other people. So
What
yeah,
a,
it was really learning.
what about the perseverance or the capacity to stick to challenges or to approach them, right? Because when you, particularly in a science field, there's a lot of low days, right? There's a lot of times when your experiments don't work as you expect, or you know, there's a lot of unexpected results and a lot of disappointment, and you need to just carry through. Do you think this is giving you an edge?
Yeah, yeah. I mean, definitely. So think about, so when, so in my masters, for example, I had a master's advisor, and then in my PhD advisor, and then I had another advisor for my postdoctoral studies. Each of these people really taught me something that's extremely important. So, for example, when I was in my PhD, at some point I had very low patience towards a certain research area. Like I had a lot of problems, and you know, in terms of like my science didn't work for a year. You know,
Yeah.
it's horrible, right? So it's really tough, because a year, like you take, usually in the first year you take courses, and then you only have 3 or 4 years maximum for your research, like, and you have to make a conclusion, you have to make a story. um, so losing about a year of that, that was not easy. So I didn't lose it. I would say I learned a lot in terms of organic synthesis, but I didn't get results that were part of my thesis, at least in that year. But my advisor really taught me how to be really patient.
Yeah.
So patience was something. So from each of these people, I really learned something that kind of shaped me who I am now. Because each of, like, for example, when I went to William Dictel lab, the nice thing about the way Will Dictail thinks is basically he's very he thinks about impact, he thinks about practical research, he thinks about, like, okay, how we can make the synthesis much shorter and much more impactful, much more practical for industrial point of view. This is something that was amazing, because like in my PhD I was focused on learning skills of organic synthesis and supramolecular polymers. So we used to make some synthesis of 17-step synthesis. We know that you know, that's very difficult to take to industrial, like, you know, setup. But in my postdoctoral studies, was the opposite, right? So it was like, oh, okay, let's do things 1-2 steps maximum, get very exciting materials that can really solve a big problem, and that will be the impactful thing. So I would say perseverance in terms of like the patience I learned from my PhD, but then I, you know, built on that skill when I went to my postdoc and then my industry, to be more practical, to be more impactful. And so yeah, so working for different advisors, you know, every advisor have their own kind of like thing. So learning the best kind of skill from your advisor really kind of you know, it's like a pieces of the puzzle you put together, and then it shapes you who you are over time.
It's beautiful, Aladdin. You have described it so nicely. So there's the courage and the family example and encouragement in your story. There's the you know, this sort of going through a process of overcoming challenges and having the courage of going finding the challenges and addressing them and leaving them. And then is you know, the impact of the mentors, the people you meet, and then being able to take home their messages, right? And learning something, and you know, and just growing as a person organically like that. It's beautiful the way hearing you describing it, and I was also kind of fascinated about how you caught immediately the the different approach between doing academic and industrial research. So the the sort of like exploration and sort of the intellectual challenge of the academic research on one hand, and the pragmatism of looking for an actual application that you can sell in industry, and how you look at that thing. Did you realize this before deciding to move into industry, or is it something that you kind of learn after you started doing industrial work? Just a curiosity.
Yeah, that's a very good question. So I think I would say maybe the major kind of changer for me was working with, again, like with Dictate's lab. I think the kind of teaching of how kind of like practicality and the impact of the work. I think that was the very first, kind of like environment that somehow shaped me a little bit or prepared me for industry. Because like in general, to be honest, even when I was a PhD, I was not really interested that much in becoming a professor. Because I knew that I really wanted, like, I like to work on the front end of the research, like, making things that have impact, that have like, people would, see the result of what I'm doing. I don't want to be working on things that are very, very long term or just like, so I would say working with Will Dictel was really kind of like the amazing kind of experience that I had before I had a transition to industry, because like, again, like the mentality of the group was really nice in that perspective, and that probably one of the reasons why I choose even working with Will Dictel in the first place is because I saw also most of his work was centered around covering organic frameworks, which are made in 1 or 2 steps maximum. So I really like that. You can make quickly materials, and then you can see their nice application, and then you can really see the influence or the impact of these materials. So then when I went to industry, I was better prepared for it. So then I think even in Arkema in the very first year, I really focused, like there was some challenges. Maybe probably we can talk about that a little bit later, but there were some challenges in Ilium, for example. The resin that I was part of a team that developed that resin. So there were some challenges in there, and I really kind of like the way that I approached that is thinking somehow outside the box, and let's try to make some technologies that are not going to affect the mechanical properties of that particular composite material. And I really thought about immediately, the first thing I thought about is I don't want to make new things like in the lab. I want to look at commercial kind of materials, leverage some chemicals that are already in the markets, and try to see if we can have some of these chemicals solve these problems. That was very practical, because like if you can do that, you are already starting with commercial material instead of really developing something new, making some new molecules. It's going to be higher hurdle to really kind of apply that type of research. Whereas if you start with something that's more kind of already is available in the market, solve a problem, and then that it's going to go to market much faster. So I think that really kind of, I was already really ready for industrial setup right after kind of Will Dictel's lab. I think that really grew even more over time.
That makes perfect sense. So you're speaking about pragmatism in the research approach. You're speaking about being driven by the result of your work, right? Rather than the intellectual challenges per se. But of course, as every scientist, you're a problem solver, right? And that is probably where you take your creativity and imagination. And I really like to go there, if you don't mind, because sure. I found it really, really interesting the way you were speaking about imagination, and obviously there were a lot of interesting angles in your presentation, but I like the passion that you were showing, which is something that I always pay a lot of attention to. So how do you put all these pieces together, right? The being imaginative and pragmatic at the same time, or being a problem solver, but ensuring that something is practical, it becomes something usable, which is key for an industrial research. Can we discuss about some of these aspects?
Sure. Yeah, that's great. So in terms of the imagination, I think that what really helped. I'm a visual person.
Okay.
So the way that I usually so kind of look at things is more like, I have a lot of imagination in terms of like looking at things and try to imagine things in the kind of like really three-dimensional space in my mind, that I kind of think like, even when I used to study chemistry, the only way that I was able to understand equations is by imagining how molecules in the three dimensions, their structure, and they are reacting with each other. This is how I used to memorize the equations and the results. I can't really memorize things by just like, looking at the text, and just I can't do that. Imagination was a huge part of the way I think in general, and I really think to be like, imagination is a really one of the most powerful skills that you need to have if you are going to be a successful scientist, because knowledge is amazing, right? So you can learn, you can memorize things, you can read more research, but if you would like to make a step up performance in something, if you want to make a breakthrough in something, you knowledge is not enough, right? Because your knowledge is only what you already have now, right? But if you would like to make something like a breakthrough, you have to step out of the kind of current kind of knowledge barrier, that's in the field you are working on. So you have to have imagination to be able to kind of step out, like think outside the box and step out of that barrier or boundary, and then you can push that boundary even farther, and then you can provide some kind of a new perspective or new angle at looking at things. You have to have imagination, and I think the best scientists, over in the history, were all kind of like imaginative, highly imaginative. Like they were thinking about like the advances in space. Like humanity wouldn't be able to really go in like into exploring moon, or going even farther, if they don't have this imagination. Like imagination is really kind of the driver, and the kind of the mindset you need to have to be able to really make a breakthrough discoveries and solving big problems. So that's kind of the imagination side of the thing. And then if you really couple that with, as you said, pragmatism and practicality, and how, like, thinking about things that are more applicable and that can be more easily adapted by like industry, and then can be translated into products. If you couple these two together, I think that you can really make something very powerful.
How does your brain work, Khalid? Are you is your imagination an instinctive one? So, are you someone you just get ideas, and you wake up at night and you say, "Oh, this is how I could do it," or are you more of a systematic type of imaginative person, where preparation really pays off?
Yeah, so preparation is I would say both. So in the first step, I take kind of systematic approach on learning about the problem that I'm working in, because as you can imagine, I worked on different problems over time, and then so you need to kind of like have some knowledge also to be able to step into a certain area. So you have to take some systematic approach, right? So you need to kind of go in broad in the whole field, read about it, understand about it, and then go kind of deeper and deeper to understand more about the problem you are trying to solve. So that needs some planning. That needs some kind of like preparation and a more systematic approach on kind of like building up that knowledge. But then once you are in an area where, okay, you understand what has been done before and what's the current problem is, that's when after that I kind of let imagination go. Then I would sit, okay, and then probably I take a couple of weeks just like keep thinking about, okay, how we can kind of like solving this problem without compromising some other aspects of that problem that we need. So that's so probably imagination is kind of the last piece that you need to put in there to be able to really bring up some innovative idea so that you can solve that problem and make a breakthrough in that area, particular area. So yeah,
and this is difficult to describe, right? Because I know these are talented people like yourself.
Thank you.
It just happened, right? It just happened to you. It's kind of in your head somehow, and it comes out, and sometimes you don't even know how. And of course, the preparation plays a key role, because so if you have control of your situation, it's obviously easier to be creative. But sometimes you just need to see it, and some people do, and some people don't. And I can see that. It's fascinating to me though, because if you put 10 people on a given project, right? Probably half of them are going to come out with a very similar approach, but if 5 people might look at it from a completely different perspective, and it's really hard to predict. So it's refreshing to think that even in an industrial setting where there's a lot of data and a lot of control over experiments, right? There's still the human factor playing a role. How do you fuel your imagination though? Where do you find inspirations? Because you kind of need to keep this in motion, right? It's something that you need to train in a way, isn't it?
Yeah, that's totally true. To be honest, the way probably it's just like I think, and again, it's not only me. I mean, I've seen a lot of really very creative people in the industry. Most of the people I work with, I mean, it takes a lot of, as you said, it's we have constant discussions, we have brainstorming sessions, and it's like there is no way like all the time that I come up with only like many other people like sometimes inspire me with a lot of nice ideas. Even in Arkema, some ideas that I came up with, my manager was a big inspiration in terms of like what's the direction I should think, in which direction I should think about solving that particular problem. It's the same thing in DuPont now. So I would say it's not just like one person thing. It's really a highly collaborative thing. You need to have a lot of like brainstorming and kind of discuss with people. Sometimes like a simple kind of mention of a simple idea from a person can really inspire you to think about something completely different than what you were thinking before. So it's not only like all the time comes just from one person. It's always coming from constant discussions and having like more dialogues and sometimes inspiration. So believe it or not, so like there was one of the ideas that I thought about when in one of the companies I worked for. So I don't want to mention details, but I was inspired by metalloproteins.
Okay.
Just something completely different than I'm working on polymers. Things are but then it's just like I was one day I was looking at a kind of like a documentary, and I saw these metalloproteins and how iron or copper kind of like is coordinated within the kind of the bioactive regions. It just fascinated me how these metals kind of interact with the environment, and I was inspired by that. And then I came up with an idea, and the next day I couldn't sleep at night. I think I stayed up about like 3 or 4 hours, and I was just digging more and more, and I came up with some ideas that are even based on some materials that are already in the market, and that paid off highly. Like it brought a huge new perspective actually into that project. It was just something by chance that I saw that I had no idea about before. But yeah, sometimes like, and I've seen that in many scientists. Like I would say most of the scientists I work with, actually in industry especially,
I like
they
that.
think that
they
way.
Wake up at night.
Yeah.
So,
you just your brain kind of
going.
continues working.
Yeah,
You can't stop it.
No, I understand, and I'm actually glad you mentioned the example, because that's how I described it at the beginning, right? So whether you're one of these people who just get ideas out of the blue in the middle of the night, and apparently you really are.
There is inspirations always.
and it's good, honestly, we have done interviews for this podcast now for a while, and it's a privilege because it gets me to speak with a lot of talented people and a lot of creative, ingenious people, but also extremely prepared and coming from very different cultural angles. But this comes across a lot, and I'm kind of jealous, I suppose. I don't know. Anyway, it's I like to jump into some of the details of your work, because you've done a lot of different things, right? And maybe we cannot touch them all, but probably discussing a bit more of the problems and the chemistries, your polymers you'll be working on in your career. We can get a glimpse of your creative process, and it would be really fascinating. So I don't know, do you want to start from what you did at with Dictel, with your Cycledextrin polymers, and that seems like an interesting enough idea to discuss. And
I totally agree, because I'm very I can't discuss everything about it, right? Because it's published and it's
exactly.
So it's I think it's a perfect start to talk about that. It's so we got a big grant actually from NSF at that time to work on making some sustainable polymers, because I was part of also the Center for Sustainable Polymer in the University of Minnesota, which is funded by NSF. So the motivation for that particular grant was really to kind of was given to Will Dechtel to really develop some sustainable materials for solving some big problems. It was just like an open thing. It was up to us to think about like which kind of application or which area we should think about. But then I think it was kind of like probably in about a month of time, constant discussion between me and Will Dechtel that we came kind of like it was kind of we thought about like cyclodextrin, because we know cyclodextrin is a very sustainable material. It has a huge application everywhere, and I think also we know that it's being used for water purification. But during that kind of months of discussion, we found out that there's like a gap there. There's never been any high surface area cyclodextrin polymer before, and Will Dechtel lab is really specialized in making porous polymers, right? But the hurdle was that you can't use cyclodextrin and make a organic framework with it. You can't do that. It doesn't have the geometry that allows you to do it. So you need to think about like a really randomly kind of like porous high surface area polymers, and we haven't done that much like that in Will Dechtel's lab. And that was actually came that we need to develop a chemistry for it. We need to develop a reaction. We need to think about crosslinker. What is the crosslinker that would enable us? So that's where I kind of really dig into the kind of literature and kind of like really understanding what has been done in there, what are the linkages that have been kind of used with cyclodextrin, what's also the cross-linkers. And I really realized that there's a gap in there, that all of these, either the cross-linker or the linkages, are relatively long or flexible. So flexible meaning that they have really kind of like a rotational kind of freedom around them. So you can imagine when you have a network where you have kind of the cross-linker or the linkages are flexible, like the monomer is freely kind of to rotate and adapt a different conformation. Then if you have your adsorbent materials, like you think about beads, for example, they swell in water, right? So then you have a little bit of a porosity around them. But then if you try to dry them, they just collapse because your network is very flexible, right? Because monomers can really kind of like rotate, and they will adapt they will try to reduce that free space inside them. Now, the only way to be able to lock that is to have a very rigid network from inside. And that's actually where the bricks game came into my mind, that you need to think about like, these type of non-complementary shape pieces.
Like Tetris. Like
exactly.
Tetris, yeah, okay.
Exactly. So basically, if you play with that game very quickly and without really carefully kind of reorienting those pieces, they will just drop randomly, and then you will have lots of voids inside them, right? Yeah. So you need to do that. Actually, it's the same thing in chemistry. You need to do this reaction very rapidly, and you need to have these building blocks very rigid. They react randomly, and then you don't give them time to really kind of reorganize into kind of a more thermodynamically stable.
So you approach your chemistry like a crappy Tetris player, like myself. It's great.
Exactly. Yeah, exactly. That was really the big inspiration behind that, and that's why I started reading literature and trying to find a cross-linker. I want to have a direct linkage with cyclodextrin. I don't want to have, like, for example, if you have an ester, you have two bonds between the two monomers. If you have an ester, right? I want not two bonds, sorry, like two atoms, right? So I want to have just one atom in between the two monomers to really minimize that kind of rotational freedom. And that's why tetrafluorodiethylnitrile was really interesting to me, because it can react, like if we can react with cyclodextrin, then the oxygen of like the hydroxyls on the cyclodextrin can attack that ring, do the nucleophilic aromatic substitution, kick off the fluorines, and you have a direct linkage in there with an aromatic ring that's very rigid. That's actually, then in this case, you have a very rigid network in that way. And
Aladdin, let me do a step back, just for someone who might not be familiar with the chemistry of cyclodextrin. So cyclodextrins are polymers of carbohydrates, right? They are cyclic carbohydrates pretty much. So they are basically full of hydroxyl groups around, isn't it?
Yes, that's true.
Is this what makes for their highly absorption capabilities? Is it like hydrogen bonding type of things with the OH?
It's actually, yeah. So in terms of the chemical structure itself, right? So it's similar to cellulose, right? But if you compare cellulose, for example, or glucose with beta-cyclodextrin, the cyclodextrin is way better. Cellulose doesn't take uptake. So the reason for that is because the beta cyclodextrin has kind of a cup-like structure. I don't know if so it has a large kind of like diameter kind of like right. So it has, it's really like a cup that's kind of it goes like a cone kind of type of structure. So the kind of the larger inner kind of like diameter, I would say a cup side of it, enables it to really form kind of host gas complex with organic molecules, because the inside that cup is hydrophobic, outside that cup is hydrophilic, right? So that's why the many of the organic pollutants have lots of kind of hydrophobic parts on them that does not like water, and that's why they go inside this cup, because they like it. Exactly. So it forms this kind of complex because of its like stereo structure. That's what makes it really amazing for sequestering organic materials.
Thank you. And so you were looking at cross-linking together these monomers of cyclodextrins and make a orderly, or more or less, three-dimensional structure with it. So the idea was, from the chemical perspective, doing a cross-linking between whatever OH groups you had on the surface of that, isn't it?
Exactly.
Okay,
exactly.
Perfect. Yeah. Then we can go back to your chemistry for the cross-linking. That was interesting.
Sure. Yeah. So we decided about tetrafluoroethylnitrile. The hurdle was actually that there has never been any reaction or like the nucleophilic aromatic substitution reaction between aliphatic hydroxyls and the aromatic fluorides.
Okay.
There's there were some polymers with catechol type of like where you have like phenolic kind of like oxygens on a phenyl ring.
Yeah.
This, you can imagine, this is more nucleophilic, right? Because like it's the acidity is much higher basically. For the hydroxyls, the acidity is much lower, so it's not easy to provide a nucleophilic oxygen to really be able to do the nucleophilic aromatic substitution reaction. So that was a new kind of that was a challenge for us, and that's why I spent a little bit of like some time to develop this reaction, to try to find what are the bases that I can really kind of drive this reaction, where I can remove that proton from the hydroxyl on the cyclodextrin, and then allow the cyclodextrin to really attack the aromatic ring or the aromatic fluoride, and then kick off the fluorides from that. And then you need to stabilize also the fluoride anions that are a result of that reaction. So that's kind of even thinking about like what's the medium that you need to have, because like if you do this reaction in water, you cannot do it, right? Because water can interfere in the reaction. You need to have a protic solvent that does not participate in the reaction. So they think about THF was good in that regard, but cyclodextrin is not soluble in THF. That's another problem. And that's why actually in the very first kind of type of material we made, the yield was lower than 20%. It was very low yield. But because the material was extremely interesting, that paper got into Nature because like it was just something really like very new reaction, very new type of material that solved big problem. But then in the later papers that we had, we improved that. We added a binary mix like solvent of the THF with DMF, so that we improved the solubility a little bit of cyclodextrin, and so that's why you were able to do the reaction more in homogeneous conditions where you can have a higher yield. We were able to boost that yield up a little bit.
So I suppose that in these polymerization experiments, you need to do it in a very controlled way, because you were speaking about doing it quickly so that you actually form gaps in it, but you want to control the three-dimensional structure of it a little bit. Otherwise, the properties would be altered, I suppose.
Yeah, that's true. So the reaction takes about 2 days, and the reason for that is because it's heterogeneous. So the cyclodextrin is not soluble. But once, so the way you can really control, like really lock the structure, is by having irreversible reaction. Okay. And the nice thing about this nucleophilic aromatic substitution reaction, it's irreversible. Like once it's reacting, there's no way you can. It's an ether bond, right? So it's very, very difficult to break that bond. So that's the nice thing about it. So I would say that's the opposite to what Dechtel's lab was doing, which is like the covalent organic frameworks. They were kind of really trying always to use like linkages that are reversible, because you want the covalent organic frameworks to be more crystalline, and they, if you have an error during the polymerization, you want that error to be corrected over time. Yeah. Here we are doing the opposite. So we are trying to do this, the irreversible linkage, and that's the nice thing. Like why I choose tetrafluoroethylnitrile is because the nucleophilic aromatic substitution reaction it's not reversible. So I wanted by design that this reaction to be irreversible, so that we can have like a very quick trapping of the whatever the structure or the pores that you formed in the first place.
So this is applied for remediation, right? Removing pollutants from water or even air, I suppose. So how stable are these materials in the sort of even potentially harsh conditions, right, of a real life application?
Yeah, it's very stable. It's very stable. So we've subjected this type of polymer, like that was one of the difficulties, is how to characterize that, right? It's the solid, like it's insoluble in anything, even if you heat it in DMSO. So it does not break.
Nice.
So that was really highly stable material, and most of the NMR characterization is all done in the solid state NMR. Even fluorine NMRs that we've done, carbon NMR, whatever, it's all in the solid state. You can. There's no way you can really get that into solution and then you can characterize it. So it's highly stable. That's
this is obviously very high potential materials, right? So are they currently having any commercial application already?
Yeah. So this work resulted in the startup of a company called Cyclopure in 2017. The company has re-diversified these materials. It developed several new kind of like versions of that polymer, or even like for different applications. So it's already doing really well. I can't really speak too much on that, so I don't much know about what they are doing in details. But also the enough details I know. I think it's not yet kind of like allowed to be discussed, but in general there's a lot of like really kind of collaborations with like overseas, even with different countries, like water facilities and stuff like that, big companies, and this material really kind of received a lot of attention in that regard. And that actually that particular company also got the award from Chemical Engineering News in 2019 as one of the top 10 startups to watch, because already it's commercializing several products. It's already in the commercial stage now.
It must be an amazing feeling to know that you basically invented a material that as a real life application and could really be valuable and life changing. That must be an amazing feeling.
Yeah, definitely. I'm very intrigued by that, and I always go back to that story because that's my very, very first kind of strike in science. And it's like whatever I do nowadays, it's still less exciting than that particular experience. It's amazing.
Well, the first love is unforgettable, isn't it? Do you still have any involvement with the company, or now that you're in DuPont, you moved on and you just...
Yeah, so DuPont also works in the water purification space. You can't be involved like you can. So with Cyclodextrin, I'm part of the IP of that company. So I own part of the IP of that. I have some royalty in it anyway, but I'm not involved at all in any types of chemistry or any aspects of that company, because it's I'm just like part of the IP of that.
This is a great story, but you've done actually more. At Arkema, you work on the material that you used to make these wind turbines blades, which is kind of amazing. Can you tell us anything about that?
Yeah. So that was also exciting to me, right? So my first industrial experience is within the kind of like vision I had, which is sustainability. I always love to work on sustainable things. It's just like, because it's environmental thing, and it's just like my heart is always attached to this type of like trying to make something that is good to the environment as well. So the nice thing that Arkema at that time was really trying to develop a thermoplastic acrylic material that's basically has a similar mechanical property to thermosets, because like we know wind turbines are made of epoxy resins and certain polyesters, and all of these are thermosets. So once the wind turbines are used for like maybe 10 years, let's say, there's a crack in them, something like that, there's a huge amount of plastics that is just unfortunately being not being used again, and there's no way you can recycle that. So the nice thing that here with my work in Arkema is that I worked in a team that was really aiming to develop the very first recyclable wind turbine, like thermoplastic, where you can thermo shape it, and you can even not only thermoformable, but so basically you can heat it and then you can make it different shapes. So that's kind of part of kind of recyclability. But also Arkema did beyond that they were able also to find a way to depolymerize that, so that you can heat that, like you can heat that composite, and you can really break the polymer back to the monomer level. That's really fascinating. And I'm really happy to have been part of that big project, and it really worked very well. And that material got commercialized the year almost the year I left Arkema in 2018, at the end of 2018 almost. So yeah, I really enjoyed it. It's just like when you work in an area where also you feel that it's part of your vision, I think you would have more energy to work on it, and you will have more enthusiasm. So
So you said that chemically these are polyacrylic type of polymers?
yeah, yeah, they are acrylic based, radical polymerization.
So what was your role in the project?
Yeah, so actually when I came there, so partially is optimizing the kinetics, like the polymerization kinetics, the initiator package, that you need to, because you need to add some like peroxides, right? So
Yeah.
you can, like, you need to. So I was part of, like, partially I was working on optimizing kinetics, and also there are some structural defects that so in that composite material, or even in the resin itself, that I think played a huge kind of role in solving, or kind of removing these kind of structural defects that were really kind of somehow delaying the commercialization of that material. So yeah, so yeah, from different perspectives, I like a perspective that I would say, like, I worked on that problem, and yeah, it played really well.
And then now you work on yet a completely different application, right? Now you're working on this technology, which is called chemical mechanical planarization, which is used in the manufacturing of microchips. And by the way, this is something that we have discussed in, I think it was episode 4 of series 1. So I invite the audience to go and check. But we actually put the attention back then to the slurries. But you actually work on the pad part of the technology. And also chemically, it's completely different. So these are polyurethane type of polymers, aren't they?
Yeah.
So it's an incredibly diverse career, and I'd love if you could tell us a bit more about that. Maybe starting from a bit of a description of what chemical mechanical planarization is.
Sure. Yeah, yeah, I would love to do it. So, CMP is a process used throughout the chip fabrication process. So, as we know that the chips are made on kind of a silicon wafer, so it's kind of like, the type of discs, right? They can be like 200 millimeter wide, and or in diameter. Each wafer contains really hundreds of chips in it, that are built in it. So you kind of use, you build the chip, or in terms of the fabrication on that wafer, and then after that you dice the kind of the chips from the wafer, and that you get your chips, and then you can package whatever you can do with it. So throughout this chip fabrication, so when you usually, like, if you look at the cross section of the chip, you would see really kind of layers of like different metals. They could be tungsten, they could be copper, they could be, like a lot of different materials, that are kind of built into the chip itself. And then you have the semiconductor also layers in it. And they are very complicated. So these layers are built sequentially. So they are not just all, like, sometimes you have 30 layers in total. So it's really multi-step process of fabricating it. So when you deposit the kind of the layers, you need to all the time, you need to really planarize the surface, because you always, like, you cannot easily control the deposition of the kind of like materials, either the metal or the semiconductor on the chip, on the kind of after lithography, right? After you make the pattern that you would like to have. So then, so after you deposit the new layer, let's say, you always have excess material in areas that you don't want this material to be in. That's why you need to planarize. You need to kind of really remove the excess material from the kind of like areas that you don't want this excess. Like you want basically to have really fine tuning over or control over the kind of I would say the what's called remember. The pattern that you have in there, right? So you want to have really kind of like the accurate kind of like, or accurately printing the micro scale features on the on the chip, right? So the features, so let's call them the features. So you can't do that without with any methods. That you have to use CMP in there to really planarize and have the feature kind of like the fine tuning of, or the fine control of the feature shape or dimensions on the chip itself. So So we apply this process multiple times, and then sometimes like 30 times throughout the, if you are making 30 different layers, for example, just like for simplification.
So
So this
and the way they work is like a very sophisticated sanding machine, right? So you
yeah.
use it's a wet sanding of this surface, and you achieve nanometric resolutions, type of a few nanometers kind of precision.
Yeah,
which
exactly.
is kind of mind blowing.
Yeah. It's highly complicated process, and there's a lot going inside this process. I mean, there's like a lot of process variables. There's like, as you said, the slurry in there is like a huge amount of variables in there, right? So you have the abrasives that you are in there, the abrasive sites and the abrasive concentration and the pH of the solution, the additives you add to stabilize these abrasives, the also to control the interaction of these abrasives with the wafer and with the pad. All of that also in the slurry solution is like a lot of different variables, and in the pad it's another whole dimension of also complexity,
because the planarization happens for mechanical but abrasion, but also there's also a chemical phenomenon, right? And so you work on the materials used for these pads, which is basically the material that creates the friction, right? And between basically that you got your wafer, the microchip, you have your slurry in between, and then you have your pads that they probably rotate in some way, and that's the way you create this mechanical friction. And I suppose you need to have different types of materials in chemical nature or in softness or in whatever features, depending on the type of chips and materials that compose the microprocessor, I suppose, isn't it?
Yeah, that's true. So there's as you said, so there is the kind of material properties side of the pads, right? Which is, as you said, like the softness, and you got you can talk about the tensile properties, compressive properties. Also we had like some porosity in them, because these are like really hard forms or soft forms, right? Some of them are elastomers, some of them are more like thermosets, some of them are thermoplastics. It's a huge variety of different materials, because you need also to have them being kind of in terms of like the fracture mechanics of that is also a very important part of the pad, because that affects on defectivity, right? Like the defects that you see on the wafer. So you need to make sure also you don't generate too many debris from the pad itself because of that friction process. So you have that. You have also the surface properties in terms of the chemical properties of the material itself, because it can also the way it interacts with the slurry abrasive particles, because like sometimes the abrasive particles tend to agglomerate or adhere on the surface of the pad for some reason. Sometimes you would like them to be more like, no, you don't want them to adhere on the pad. You want them to more be attracted to the wafer surface. Things like that. So that's also the chemical properties of the surface. There's a grooving also. I don't know if you've seen like the polishing pads. They have like grooving kind of patterns on them. So the grooving also like
it's like a tire, like of a car. That's
exactly,
the way I imagine.
Exactly. It's like a tire, right? So it's exactly like that, right? Because it can have hydroplaning. You would like to have more friction, so you control this type of friction, kind of like physics on the pad during the polishing process. So the grooving pattern or grooving morphology or design affects on the speed and the flow direction of the slurry on the pad during the polishing process, and that has a huge effect on the polishing rate, on the defectivity, like the way you kind of really direct your debris to go in that direction, away from the wafer or towards the wafer, vice versa, things like that. So it's all of that. Like, think about how complicated that process is. It has a lot of complications.
And developing the polymerization to have like the level of precision necessary to planarize something, of a few nanometers precision level, that must be crazy. So I suppose you work on controlling a huge number of variables during the polymerization process, and probably you need to create different materials depending on the type of slurry or the type of microchip that has to be worked right in the application. So that's a nice thing about polyurethanes. The formulation space is huge. Polyurethanes are like not only thermomechanical properties, the viscoelastic properties of polyurethane and the phase separation phenomena or phase mixing that happen is amazing. It adds like a lot of different kind of like, sometimes you can have the bulk properties similar between two materials, but they behave completely different.
because they have like some thermomechanical property, like at different temperature they behave differently, even though they behave similar at certain temperature, but at other temperature they behave differently, completely different. And yeah,
so polyurethanes are more of a family of polymers rather than being a specific. So do you have a lot of freedom in the choice of monomers that you use there?
Huge polyurethanes. It's just like I can't really emphasize how huge the formulation space is.
Yeah,
it's just like a huge area for innovation. There's no limit of like what you can add in there. There's no limit of like what properties you can derive from polyurethanes.
And I can see how the imagination here can play a key role.
Exactly. Right? Exactly. I just love working in that space, because it's just like as I told you, like sometimes like you have some bulk properties. Like what really fascinates me more is sometimes you make certain properties, you think that they would behave in a certain way, right? Because from previous experience, you know that similar paths of that particular properties behave in a certain way, but you discover that new material behave completely different. So there's something else that you need to dig more in there, and sometimes the microstructure, there's something in the microstructure makes it completely different. It's just like amazing. It's just like imagination is really a huge part of what we do in CMP.
And I suppose that in DuPont you have this sort of richness of competences and access to different types of expertise. So this is truly multidisciplinary, isn't it?
It's a hugely. So we have a lot of synergy between the different groups in terms of like the slurry and the pads, and we have lots of modeling as well. We have like it's like there's no way one scientist can think from all perspective. We all the time talk like different expertise, talk about different like the same problem. Everybody, like everyone brings kind of like the solution or the idea from his perspective, from his experience, because like it's a highly collaborative area. And I mean, let me tell you that actually, with all of the previous knowledge, and it's been more than 20 years that this process has been used in semiconductor industry, until now, probably we don't know more than 20% of how it's really going. Like how the process goes. It's even we have a lot of books on CMP, and yet it's very difficult to logically think about how you can solve a problem.
And the importance of the work is amazing, right? Because this is such an important part of a process that makes some of the things that are disrupting the world as we know it, right? So every one of us touches the product of your work pretty much every day, right? How many electronic devices do we have around? So it's amazing. So thinking that you have a role to play in that must be very exciting. By the way, the enthusiasm you speak about there makes me reluctant about asking the next question I had in mind, because I wanted to ask you whether you are always missing the sort of freedom that a more academic type of career or research might give you. Because usually in the industry, you tend to be more constrained. You have the commercial parameters that you don't necessarily have in academia. Maybe in academia, you need to ensure that you can get your next funding, but it's a different type of things, right? But from the way you're describing what you do, it doesn't seem that you miss that at all.
Yeah. So I would say so. So maybe different people from different industries have different experiences, but at least in my situation in Arkema and DuPont, I did not have this problem. To be honest, there's lots of freedom around what research we do. At least the people, the managers I work with are very open-minded, and probably, this is the nice thing about big companies is they have like, if you have some ideas, and if you like, they also have a lot of programs around fundamentals. Like most of my work has really focused on fundamental structure property relationship of polyurethanes. It's because like they have the capacity for that. They would like to build on knowledge, and they would like to really improve their kind of understanding and their ability to tune the structure and the properties. So that gives you a lot of freedom in terms of the science that you can do. And I had like even a couple of years I was working just on really expanding the material toolkit of some of the parts we have, and I had tremendous freedom in there, a lot of resources, no issues at all with that. And that was really amazing. The same thing in Arkema, they have a lot of like tolerance, and they even actually encourage their scientists to even more think about like how you can dive deep into the research problem, not just like solve it on the surface and then not understand really how you solved it. They would like really to understand why. It's because like when you understand more, you can do more, and you can have more, like, better. So at least in my experience in these two companies, I haven't had this problem. It's like a mix between academic and industrial research together, and that really, I enjoyed it.
And you probably come with the right mindset, right? Because we spoke about your pragmatism and how you like things that make sense. You don't want to be too Byzantine in your research. You want to be to the point. You care about the applications, and it probably makes you a good fit as well. So you probably have a good personal component there that makes you effective in the job you do. So of course, congratulations for that.
Thank you very much.
This has been a really fun chat, Aladdin, and the time is flying by. And if it was for me, I would keep going, but I'm sure you have better things than spending all the weekend speaking with me. So I get to the usual final questions. All my interviews end with the same one. So obviously you are still young and an enthusiastic researcher, and I'm sure you'll face a number of new challenges, and you will have a lot of satisfaction from your career. But you have already achieved a lot, so you might be in a position to actually give advice to someone who is just starting in their career. What would that be?
Sure. Yeah. So I would say the two main advices I would give is, the first one is patience. So science is not easy. It takes long time, and we've been in this field, multiple years, like 10 or even more, just in the graduate level studies, and just building up the knowledge and the expertise takes long time. And then after that it pays off, right? So then when you start working, then you would just grasp kind of like the fruits of what you kind of seeded. So first, like patience is extremely important. The second is also trying to be more courageous, try to step out of the comfort zone as much as you can, especially in the graduate studies. Don't be afraid of that. So if you can build up that knowledge in terms of different areas, I really strongly encourage on that, because this type of skill, like the courage and being able to step easily out of the comfort zone, is very, very important in scientific research in general, and especially in industry. If you'd like to go in industrial career, you have to be able to step out of comfort zone much more easily. You can't just like be scared or be hesitant to all kind of like work on a new areas or new research. You need to be ready to do that, and you need to have the mindset to do it. So I think the courage and also step out of the comfort zone is it's a strong advice that I give to everyone. Don't be afraid of that, and try to, even if you don't have this type of like mindset, try to build it and try to learn that skill, because it's really helpful.
Aladdin, thank you very much. It's really great speaking to you today. Thanks again for being with us. This is making for a great episode, and all the best for the future.
Thank you so much, Paolo. I really enjoyed talking to you. Thank you so much. Very appreciate it. Thank you for having me. Thank you.